This week, we are reviewing quantitative research. One important aspect is to understand the statistical analysis of quantitative data. Because this is a dense chapter, there are more than the normal objectives. Let's take a look at a few of these. You're going to be describing 4 levels of measurement and identifying this for what they're used. You're going to describe characteristics of frequency distribution and interpret the various descriptive statistics. And you're going to describe the logic and purposes of hypothesis testing and interpret p-values. I want you to be able to specify appropriate applications for t-test, analysis of variance, chi-square test, and correlation coefficients, and interpret the meaning of the calculated statistics. You're going to identify several multivariate statistics and describe the situations in which they're used, identify indexes used in assessments of reliability and validity, and understand the results of simple statistical procedures. Let's begin by reviewing the level of measurement. Nominal measurement is categorical data, and it uses numbers, but only as attributes, such as a male is 1 and a female is 2. Ordinal measurements rank an attribute. 1 would be they completely agree, 2 they partially agree, 3 they don't agree at all. Interval measurement is about rank, and it provides a distance between attributes. Scores on an assessment exam would be an example. Ratio measurement is something that has an absolute meaningful 0 and provides information that about the absolute magnitude of the attribute, such as height and weight. Variables in interval and ratio data are often called continuous variables. Some statistics are only used to describe data, that is, descriptive statistics. We do calculations on data to make inferences about what was found and apply those findings to broader populations. This is referred to as inferential statistics. There are 3 characteristics of continuous variables: values, central tendency, and variability. Frequency distributions are an arrangement of values from lowest to highest and account a percentage of how many times each value occurred. N would equal the total sample size. There are several ways you will see this data. This is one of the ways. You will notice there's a score, a frequency, and a percentage. So a score of 15 occurred once, while a score of 25 occurred 7 times. And then it gives you the percentage. The N at the bottom is the total number of participants, and then you have the total percentage, which should always add up to 100%. Another way to look at this is on this graph, and you will notice that 15, a score of 15, has a frequency of 1, whereas a score of 24 has a frequency of 9. Examples, we also describe distributions by their shapes. A symmetric distribution has one peak and is equal on both sides, such as you see here in A. It is equal on both sides, it has one peak. If the peak is off-center, then it is referred to as asymmetric and skewed with the tail longer on one side than the other. If the tail points to the left, it's considered a negative skew. And if the tail points to the right, it's considered a positive skew. A unimodal distribution has one peak. This is a unimodal distribution. It also happens to be a bell-shaped curve. A bimodal distribution has 2 peaks, and you can see that here. We often want to know what is most common. How many calories does the average patient in a nursing home need each day? The single answer we want is central tendency. There are three indexes of central tendency: the mode, which occurs most often, the median, which is the middle point, and the mean, which is the average. Variability refers to how spread out a distribution or data points are. Even if I have two sets of data with the same mean, they may be distributed differently. Here's an example for us. In table 13.4 in your textbook, you have an example, A and B. The mean for both A and B are the same. So the mean of these two is the same, even though they don't look alike. You will notice that in A, the score goes down to less than 65 and above 135. And in B, the score is closer together. It is above 75 and below 140 and below 130. The closer things are together like this, the more homogeneous or the more alike they are. The more spread out they are, the more heterogeneous they are. To know the range, you take the highest number, and in this case, this would be about 140 minus the lowest number, about 60, and the range would be 80, which is 140 minus 60 equals 80. Can you do that for B? Take a minute and stop the recording and try it. Yes, B is 125 minus 75, so the range is 50. Standard deviation is the most widely used variability index. It summarizes the average amount of deviation of values from the mean. You will frequently see this in articles as a capital N, the mean score, and then a plus or minus, a capital S, capital D, which is standard deviation. What is standard deviation? In a normal distribution, there are three standard deviations above, 1 plus 2 plus 3, and 3 below, minus 1 standard deviation, minus 2 standard deviations, and minus 3 standard deviations. Let's look at figure 13.5 from your textbook. 68% of the cases are between 1 standard deviation. 34 here, 34 here, minus 1 plus 1 is 68%. 95% are within 2 standard deviations. You see the plus 2 and the minus 2, and you add all these percentages together. 13.6, 34.1, 34.1, and 13.6. And 99.7% are between 3 standard deviations, minus 3 and plus 3. And again, you would add everything together. Bivariate descriptive statistics describe the relationship between two variables. It basically describes the intensity and direction of a relationship. There are two things we'll discuss: cross tabulations, a two-dimensional frequency distribution in which the frequency of two variables are cross-tabbed, and correlation, which is the relationship between two variables. Let's take a look at table 13.3 in your book, which is a cross-tabs table for relationships between gender and smoking. Gender, right here, is nominal data. They're just counting the number of men and the number of women. Smoking is ordinal data. They're looking at non-smokers, light smokers, and heavy smokers. See, this is ordered. Then they're just counting the number of people that identify with each of these groups, and they're giving that a percentage of the total. So they would look at 22's the total, 10's the number of smokers. That was 45.4% 84% of women are non-smokers. They do the same for the men. Then they take the numbers and they change these into percentages and compare them. You compare the percentage of men to percentage of women in each of these groups. In correlations, we are asking to what extent two variables are related to each other. A correlation coefficient describes the intensity and direction of a relationship. The correlation coefficient can range from -1 to +1. Negative relationships are 0 to -1, so minus is negative. And this means that one variable increases as the other decreases. An example of this is exercise and weight. As your exercise increases, your weight decreases. A positive relationship is from 0 to +1, so plus is positive. Both variables increase. So as I increase my calorie consumption, my weight increases. The greater the absolute value of the coefficient, the stronger the relationship, which means the higher the number, the stronger the relationship. So we do this as R equals, and an R equals a -0.45 is stronger than an R equals a +0.4. And I know that can sometimes be confusing, but it's the size of the number. And 45 is a bigger number than 40. When variables are not related, the correlation coefficient is 0. Now there are two other things to think about. Pearson's R, this is the most widely used and is composed of continuous data. And Spearman's Rho, and it's used for correlations between variables measured on an ordinal scale. Evidence-based practice, when we're thinking about risk, we do that a lot in evidence-based practice. And evidence-based practice makes decisions based on the existing research. Part of the calculation is risk before and after an intervention. And some of the more common indexes are absolute risk reduction, odds ratio, and the number needed to treat. If you take a look at table 13.4 in your text, there's an example of desirable and undesirable outcomes. Absolute risk is the proportion of participants that experience an undesirable outcome in each group. Thus, the index is the estimated proportion of people who would not have had the undesirable outcome, though exposed to the intervention. An odds ratio is the proportion of people with the adverse outcome relative to those without it. So we're comparing the people with the adverse outcome to the people without it. And a finally important is index of risk is the number needed to treat. And in healthcare and in medical research, this is really important. In your textbook example, this is the number of people you would need to receive an intervention to prevent one undesirable outcome. Inferential statistics is based on the law of probability, and it provides a means for drawing inferences about a population given data from a sample. It's used to test a research hypothesis, and it assumes a random sample. Although when you're reading research articles, check this, because a lot of people ignore that it's supposed to be a random sample. It is used to make objective decisions about the population parameters using sample data, and it provides a means for drawing inferences about the population given the data from a sample based on the laws of probability. With inferential statistics, you try to reach conclusions that go beyond the data you have. For example, I may use inferential statistics to try to infer from my sample data on nurses willing to respond to a disaster what the entire population of nurses might think. Or we use inferential statistics to make judgments on the probability that observed difference between groups is a dependable one or one that might have happened by chance. Its mean equals the population mean. Its standard deviation is called the standard error of the mean. So the standard error of the mean is estimated from the standard deviation and the sample size. Let's take a little closer look at that. The standard error gives the accuracy of a sample mean by measuring the sample-to-sample variability of sample means. The standard error of the mean describes how precise the mean of a sample is as an estimate of the true mean of the population. The larger the sample, the smaller the standard error of the mean. This is to say that if we have an entire population, this is the whole population, we're never going to sample the whole population. We just don't do that. It's not feasible. So we are going to take a small sample of this population, and this should be a random selection. We look at this sample, and the standard error of the mean describes how precise the mean of this sample reflects the true mean of this entire population. Hypothesis testing, we're always interested, do we want to accept it or reject it? Remember our previous discussion about hypothesis testing? We want to know whether to accept or reject our hypothesis. Suppose we do a study and we find that the changes we expected in patient outcomes are what we did expect. We did an intervention and the patient's smoking decreased. It was what we wanted and what we expected. We hope this is due to our intervention, but it could be due to chance. To answer the question, we need to consider the types of errors. So let's look at this table. And this is figure 13.7 in your textbook. So true, the null hypothesis accepted. False, the null is rejected. And then you have the actual situation of the null hypothesis is true or false. And you can see that you have a correct decision if it's true, the null is accepted, and you're true here, that's a correct decision. And then, if the null is accepted and it's false, that is a type 2 error. If it's false and the null is rejected, but it's actually true, it's a type 1 error. And if it's false and the null is rejected and it is false, that's also a correct decision. This is going to be confusing. I would suggest when you're trying to figure this out, when you're reading an article, for a while, that you keep the table with you. The researcher calculates a test statistic and decides that the null hypothesis is either true or false. So a type 1 error is rejection of the null hypothesis when it should not be rejected. A false positive result. The risk of error is controlled by the level of significance, which is referred to as alpha. And we create an alpha of 0.05 or 0.01. Most of the time, it's 0.05. A type 2 error is failure to reject the null hypothesis when it should be rejected. That's a false negative result. The risk of this error is a false negative conclusion. And we try to address this through power. And power is the ability of a test to detect a true relationship. By convention, power should be at least 0.8. Larger samples equal greater power. And a lot of times, because of the expense of doing research, people want the smallest number they can use to get that power of 0.8. Because we don't know when we have made an error in our statistical decision making, which is why we select a level of significance, which is the probability of making a type 1 error. As we discussed last week, we usually select an alpha of 0.01 or 0.05. If we select 0.01 in 99 out of 100 cases, we would have a true null hypothesis. We would correctly accept the null hypothesis. To reduce the risk of a type 2 error again, we increase the sample size. We determine the sample size through a power analysis. And power is the ability to detect a true relationship. The minimum power we want is 0.8. Let's do a quick overview of hypothesis testing procedures. First, you select an appropriate statistical test. Then you specify the level of significance. You compute a test statistic. You determine the degrees of freedom, which is the number of observations free to vary about a parameter. And you compare the test statistic to a theoretical value. The good news is we generally use computers for our statistics now. And so all we do is step 1, and the computer does the rest. It's still important to understand the concepts in order to interpret the results, and also to know when you had a data entry error of some kind and you get a crazy, ludicrous number that you know can't be right. The bivariate statistical tests that you are likely to use are listed in Table 13.9 in your text with a detailed explanation of each. For now, I would like you to remember what is in this table. Let's review it. A t-test for independent groups. And one of the things you need to learn and you need to remember is these test statistics, because this is how people abbreviate them in research articles. So you will see a t-test, whether it's a t-test for independent groups or a t-test for paired groups, it will be a t. So for independent groups, it's used to test differences between means of two independent groups, an experimental versus a control, men versus women. The independent variable is nominal and the dependent variable is continuous data. For the paired groups, it tests the differences between the means of paired groups. So pre-test versus post-test. You essentially have the same people taking the pre-test and the post-test, so their results are paired together. And again, it's nominal independent variable and the dependent variable is continuous. The analysis of variance, which is called an ANOVA, you test the difference among the means of 3+ independent groups. Again, nominal. You will notice all these are pretty much nominal and continuous. The repeated measures ANOVA test the differences among means for the same group over time or compared to two groups over time. Pearson's correlation coefficient is used to test the existence of strength of a relationship between two variables. And chi-square test is used to test the difference in proportions in 2+ independent variables. So remember, Pearson's is the strength of relationships of two variables. Chi-square is the difference in proportions in two independent groups. Validity tells us if we are measuring what we want to measure. Let's review 3 types of validity, and there are more types of validity than this, but for now, these are the 3 I want you to remember. Content validity is how well the test measures the subject matter content and behaviors under considerations. So, you compare test content to the universe of content and the behaviors to be measured. Criterion-related validity is how well the test performance predicts future performance or estimates current performance on some valued measure other than the test itself. So we give, for example, we have you take a test if you want to go to graduate school, and that test is supposed to predict your future performance. And then you have construct validity, and that's how the test performance can be described psychologically. And the procedure is to experimentally determine what factors influence scores on a test. These are the only 3 types of validity for this course I expect you to be able to remember. But again, there are many more. And then finally, critically appraising statistical analysis. This is important when you're reading articles that you can critically appraise statistical analysis. And I would like to say people always choose the right test, but they don't. I mean, it happens. So these are guidelines, and let's review them real quickly. Did this descriptive statistics in the report sufficiently describe the major variables and the background characteristics? And were the appropriate descriptive statistics used? Were statistical analysis undertaken to assess threats to the study's validity? So did they test for selection bias or attrition bias? And this is important because sometimes people will drop out because one of the options to which you're assigned is more unpleasant than the other. Did the researcher report any inferential statistics? And you need to know, should they have reported them? Was information provided about both hypothesis testing and parameter estimation? So do you have confidence intervals? Was the effect size reported? And some people report this and some people don't, but they should always report it. Were any multivariate procedures used, and if not, should they have been used? Were the selected statistical tests appropriate given the level of measurement and variables and the nature of the hypothesis? This is probably more detailed than I'm going to expect for this course. And were the results of any statistical test significant? And this you should note, and you should note in the articles when you read them. What do the tests tell you about the plausibility of the research hypothesis, and were the effects sizable? And then you always have to look and say, okay, did then the person's conclusions match with their test results? So the other thing was the information about reliability and validity measures reported? And that should really always be reported. You need to know if somebody's using an instrument, if it's reliable and valid. And was there an appropriate amount of statistical information? So was it clear, and was it logically organized? Again, there's more videos online for you, and I will hope you take the time to look at them. Thank you.